the pleasure to introduce Damaris Meier from the University of Fribourg, who is going to talk about the uniformization of metric surfaces. Thanks.
Well, thank you very much for the opportunity to speak, and also thanks to the organizer. I've already had a wonderful time so far in this trimester program, so I really appreciate your effort. So I will talk about uniformization of metric surfaces. So most of this is based on joint work with Stefan Wenger. And yes, I think it sort of gives a good introduction into questions that are related to my research, and yes, that's why I chose this. So what's the problem that's at the core of today's talk is the following. We have given a metric space X, which is homeomorphic to some model space M, and we want to find conditions on X that guarantee the existence of a nice map U from M to X. And nice in the sense that it carries good geometric and analytic properties. So we're only interested in dimension 2, and probably most of you know a good answer to the problem in the smooth setting. Because there we know the classical uniformization theorem, which tells us that every simply connected Riemann surface is conformally equivalent to either the open unit disk, the complex plane, or the Riemann sphere. So this sort of gives the characterizations of such simply connected Riemann surfaces. And just to say, well, there the map would be conformal, and what are nice geometric properties of conformal maps? So they are conformally, they're locally by Lipschitz, and they map infinitesimal balls to balls in general. Exactly. So what we try to do today is to sort of find an analog of this statement in a non-smooth metric space world. So we're interested in metric surfaces, and just to properly define it, it's just a metric space, two-dimensional metric space. So it's homeomorphic to some smooth two-dimensional manifold M. And why are we interested in metric surfaces? So they very naturally appear, for example, as deformations of a smooth object. For example, what I have here is this origami sphere. And this is actually made out of a cylinder, and just by folding. And of course, topologically, this is still like an annulus or whatever, because we have a hole on the top, on the bottom. But one can think about sort of performing these foldings infinite amount of time, so the hole closes. And then you have topologically something that is like a ball, but it behaves like the cylinder, okay? So something like that, or also more like a quotient space. So we have a plane, and we collapse a set in the plane. It's just mapped to a point, and what happens around this one point is it gets very wrinkly. So these that might be a metric surface too, or maybe a limit of Riemannian surfaces or of a sequence of Riemannian surfaces, and in a limit a lot of singularities appear. And also another class of examples comes from boundaries of Gromov hyperbolic groups. Exactly. So these are metric surfaces, and now what is our goal of today's talk is to find conditions on X such that we find a nice parametrization. We can, of course, ask ourselves the question, well, what kind of parametrization can we look for? And maybe the first things that comes to your mind, because we want to generalize the other result, is we could look for bi-Lipschitz mappings. And there are results in terms of where the sort of the conditions on X are in terms of bounds of flatness, also existence of flat forms and curvature bounds. But somehow the general question of finding of bi-Lipschitz uniformization is extremely hard and remains widely open. So we will not talk about this today too closely, but people have been looking at that for quite some time now. What we are going to look at are other generalizations of conformal mappings. And in the first part, we're looking at quasi-symmetries. So we call a homeomorphism quasi-symmetric if it distorts shapes of sets in a controlled manner on all scales. And what I mean by that is, given any ball, when we map it, it sort of still looks like a ball in the sense that we can inscribe a circle of radius small r and circumscribe a circle of radius big R, and the ratio of the radii is uniformly bounded. So that's a hand-wifey sort of definition of what a quasi-symmetry should be. Now, the next class of mappings we're going to look at in today's talk are quasiconformal mappings. And they sort of have the same distortion property, but only on infinitesimal scales. So like conformal mappings only map infinitesimal balls to balls, they map infinitesimal balls to quasi-balls in some sense. So in Euclidean space, these classes of mappings are equivalent, and also in some other metric space settings, but not in the generality that we're going to look at today. And finally, the third class of mappings that we are interested in today's talk are weakly quasiconformal mappings. So again, we have a similar distortion property, but now it's not a homeomorphism anymore, but we're allowed to collapse sets. Okay. So this is also sort of the outline of the next part of the talk, and we start with the quasi-symmetric uniformization. So there, a really breakthrough result is due to Bonk-Kleiner from 2002, and it tells us that if we have a metric sphere, which is alpha is 2 regular, then it's quasi-symmetrically equivalent to S2 if and only if X is linearly locally contractible. So just to recall, alpha is 2 regular means that the Hausdorff 2 measure of a ball of radius r is comparable to r squared. And linear local contractibility is a condition that tells us that a ball around a point of a certain radius r is contractible in the ball of around the same point of radius lambda times r for some fixed lambda. So in particular, it prevents surfaces from having cusps, because if you think about that condition, if we pick some r, then if we go high up in the cusp, and we could pick a base point there, then the metric ball around this point is a topological annulus. And we can never contract one annulus inside another one. So we won't have cusps. For the same reason, we won't have thin bottlenecks. And it's also in some sense a connectivity condition, so it also prevents dense wrinkles. So this is a really nice theorem, just to say these conditions, of course, every metric surface that's pi-Lipschitz equivalent to S2 has to satisfy these conditions, but we could not replace the word quasi-symmetric by a bi-Lipschitz map. So there exists example of spaces that have these properties, but do not bi-Lipschitzly embed in any Euclidean space. So that's due to Laxel. And then also the theorem does not generalize to higher dimensions. There are a couple of examples by a couple of authors, and there exists alternate proof of the theorem, and also generalizations to other types of surfaces. So this is very short about this theorem. Now, one thing to mention is that alpha 2 regularity, yes?
The spheres which have cusps, so they are not 2 alpha regular, right?
They're not.
So it's a conformal dimension still 2.
I don't know. I don't know.
Okay.
Okay. So one thing to mention here is that alpha 2 regularity is not a quasi-symmetric invariant. And to see this, we can look at this mapping here. So we take the S2, the Svanich sphere, and we equip it with a metric raised to a power of alpha for some alpha between 0 and 1. This is again a metric space, and the identity mapping is a quasi-symmetry. You just scale distances in a certain way, but this space, of course, the Hausdorff 2 measure of this space is not comparable to R2, but comparable to R2 divided by alpha. And also, one other thing to mention about that is that if we would have the same statement without this alpha 2 regularity condition, then it would actually solve a conjecture in geometric group theory known as Cannon's conjecture, which tells us that if G is a Gromov hyperbolic group whose boundary at infinity is homeomorphic to the two-sphere, then it's a Kleinian group. So it admits a nice action on hyperbolic free space. Yes. So this is all I want to say about this quasi-symmetric uniformization. This also, in some sense, gives a motivation for studying these sort of uniformization results. Now, what we do is, instead of assuming alpha's 2 regularity, we now turn to the case of just having locally finite Hausdorff 2 measure. And one observation that we can make that in such a setting, by applying a co-area inequality, we can show that our space actually has a lot of rectifiable curves. And what we want to do now is to sort of find out more about the geometry of the space, and by just looking at measuring curve families in some sense. So for this, I define modulus of a curve family. And one can do that as follows. So we have a curve family gamma. And the modulus of gamma is the infimum of the L2 norm squared over some density that we put on the space. And the density is in such a way that all curves in the curve family have length more than 1. In some sense. So if we integrate rho over gamma over any locally rectifiable curve gamma in this curve family, then it should be bigger than 1. And then we take the infimum over all such curves of the L2 norm squared. So this is an outer measure on like curves in a space, and it's sort of what one can show is that if we have a mapping from R2 to R2, which is conformal, then this modulus stays invariant in the sense that the image curve family has the same modulus as the original one. So it's very natural to then define a geometrically quasi-conformal map as a map that leaves the modulus of curve families invariant up to a multiplicative constant. Now, maybe let's do a little example just to see what it is. Namely, here, well, I've already drawn the solution, but just to maybe get a feeling. So if we have a rectangle of side length A and B, and we consider the family of curves joining opposite sides, so that's gamma. And then what we observe is that any curve little gamma in gamma has length bigger than B. Okay? Now, what we can propose is to take rho as 1 over B. Okay. It for sure satisfies the second condition because of that. And well, what is the modulus of the curve family gamma is then less than integrating this over this quadrilateral, let's call that Q. So it's just the area divided by B squared. One can actually show that it's not an inequality, but an equality by sort of considering the straight line segments and applying a Forbini type argument and Hölder's inequality. So that is one example that will be important in the following of the talk. And the other example that we will make use of is this example here, where we consider the curve family of connecting a ball of radius small r to the outside of a ball of radius big R. Okay. And there it's the modulus is 2 pi times the logarithm of big R divided by small r to the power of -1. So these are the two examples that we will need. So given these two examples, we can make some observations. So if we're now in just planar R2, and we sort of multiply the modulus of the curve family connecting two horizontal sides with the modulus of the curve family connecting the vertical sides, then this is just 1. And also we can make another observation that if we look at the limit, we fix a point and let small r go to 0 and look at the limit of the modulus of this curve family here, connecting this ball with the outside of the bigger ball, then this will in fact go to 0. Okay? So this is what we, So points in some sense don't have a lot of curves going out from just one point. Now, if we have given a geometrically quasi-conformal map, then by using the Riemann mapping theorem, we can show that these two conditions hold. So one of them is that we find a constant such that the product of sort of the modulus of the curve family connecting horizontal sides of a quadrilateral times the modulus of the curve family connecting vertical sides is bounded from above and below by some kind. Now, quadrilateral, I just mean a Jordan domain with like identified 4 points identified as sort of the corner points in some sense. And the second thing is that, well, if we have a point, then this should still be 0 if we let's sort of look at all the curves going out from this one point. So we've seen R2 satisfies that, and also alpha's 2 regular metric surfaces do satisfy these two conditions. And it was then shown by Rajala that actually these conditions are not only necessary but also sufficient for characterizing metric surfaces that admit a parametrization by a geometrically quasi-conformal map. And he calls them metric surfaces satisfying this as a reciprocal metric surfaces. Now, a few comments to that. So if we've seen that if we're alpha's 2 regular, then we satisfy reciprocality, so we get the existence of a geometrically quasi-conformal map. Now, if we also assume linear local contractibility, then the quasi-conformal map upgrades to a quasi-symmetry. And therefore, we recover the theorem of Bonk and Kleiner. And the second thing is that I had these two conditions before, and the lower bound in this first condition here, this is always satisfied for some constant. And the other comment is that the upper bound here actually implies condition 2. Yes. So in particular, what we could do is we could just define reciprocality as having this one upper bound of the product of these moduli of curve families. But just to mention, in general, it's very hard to verify whether a given metric space is reciprocal or not. So we have these two conditions, or we have some conditions that imply it, but in general it's very hard. And also there exists plenty of metric surfaces that are not reciprocal. And one of them I've actually already kind of shown you here. And we're going to have a little closer look at that. So what we do is we take a disk and a small ball in the disk and we collapse this small ball. And this is then, we can equip this space with the quotient metric. And we consider the projection map pi from the disk to our metric space S. And this is a local isometry everywhere outside of this small ball that we collapsed. And it maps this small ball to just one point, x0. So now what we do is we consider the curve family connecting a ball of radius small r to the outside of the bigger ball of radius big R around this point x0. And because here, everywhere, it's a local isometry. We just know that this is the same as considering the modulus in R2 of sort of the curve family connecting around 0 of the ball of R plus epsilon connecting with the outside of the bigger ball of big R plus epsilon. And when we let here, if we let r little r go to 0, then what happens is that this will be strictly bigger than 0. And therefore, we don't satisfy the second condition, and we also won't satisfy the third one. So we can conclude that this metric surface that actually it's quite a natural construction, which is collapse set, that it does not fall into these class of reciprocal surfaces and does not admit a quasiconformal parametrization. Okay, do you have questions so far? So one can, of course, I already told you that we will look at a third class of mappings, which are known as weakly quasiconformal mappings. So for this definition, we assume that X is compact and homeomorphic to M. And then we call a continuous surjective map weakly quasiconformal if it's a uniform limit of homeomorphisms, and if we find a constant such that one of these two modulus bounds that we had before holds. So it's exactly. So we're allowed to collapse sets, but still we have a nice distortion properties. And it was then asked by Rajala and Wenger whether one can always parameterize a metric surface like that. And in case the metric surface has finite Hausdorff 2 measure, the answer to this question is yes. If we put another condition, which is that X is locally geodesic. So around every point we find a neighborhood, which every pair of points connects with a curve whose length realizes their distance. So this was work of Stefan Wenger and myself. And at the same time, when we were working at that, when we were almost finished, we were informed that Damaris and Romney were almost finished to solving the same question with a completely different approach. And so, yes, so we both published our articles. And eventually, 1 year later, they then were able to remove, with their approach, remove this condition of being locally geodesic. So just to say, this sort of finishes the story of uniformization for metric surfaces of locally finite Hausdorff 2 measure. And yes, yes, exactly. And also, if we assume that their space is reciprocal, then this map U that we get actually turns out to be a quasiconformal homeomorphism. So again, we recover all the theorems that we looked at before.
Quick question.
Yes.
Could you repeat the definition of modulus again?
Yes, go back to the definition, or?
Yeah. Okay, I see. Right.
Yes. So it's a way of measuring like curve. In other words, you can think. So it's equivalent to the capacity of a condenser. If this brings any. No. Good. Do I have other questions? Yes.
What is a map that is weakly quasiconformal but not conformal? Quasiconformal.
An example of something? Yes. This map. The projection map is weakly quasiconformal, but it's not quasiconformal.
So it's weakly because at that point, so it is quasi-conformal almost everywhere else.
So it's quasi-conformal sort of on the annulus, but because it collapses this set, it's not. I mean, we've shown here that there exists no quasi-conformal parametrization. But this map actually is weakly quasi-conformal, so it's a uniform limit of homeomorphism, and it satisfies this modulus bound also.
So we need homeomorphism, almost homeomorphism, right? In
Yes.
the definition, not.
Yeah, here it's a uniform limit of homeomorphisms.
I see. Okay.
Yes, which in this setting is equivalent to being monotone, so pre-images of points are compact. And connected. Sorry, connected. That's what I wanted to say. Yeah, connected. Thank you. Yeah. Other questions so far? Okay. Then we have a little look at the proof of this statement. So the theorem is as follows: we have X being a locally geodesic metric surface. Now we just assume it's homeomorphic to the disk to make it a bit easier. And we assume it has finite Hausdorff measure and finite boundary length. And then we want to show the existence of a weakly quasiconformal map. And the idea is sort of to make use of existence and regularity of energy minimizing Sobolev maps to create this parametrization. For the ones who have not yet seen a definition of Sobolev maps in metric spaces, this is one. So we say that a map from the disk to X is Sobolev if, when we post-compose it with a distance function to a point, it's in the classical Sobolev space W12. And we also find this H here, an L2 function, such that the absolute value of the weak differential of this post-composition is almost everywhere bounded by this H. Now again, we want to sort of construct an energy minimizer, and the energy that we're looking at here is the Reshetnik energy. And this we can define by just taking all these functions H that satisfy that, and taking the L2 norm and the infimum. So that's a valid notion of energy. If you're, yes?
And the quantifier is for every x, or the quantifier on x is?
For you pick some point x.
That exists. Okay.
Yeah.
No, I think it's for every.
Yes. Okay. It's for every. Other questions? Good. So the strategy is as follows. We first have to show or look at a sort of a set of mappings, candidates that we want. So we want Sobolev maps from the disk to X whose trace is an almost parametrization of the boundary in the sense that it's a uniform limit of homeomorphisms from S1 to X. And yes, so the first step is, of course, to show that this set is non-empty. And maybe I have to just mention this is fairly non-trivial. It could happen that our metric surface X contains a countably two rectifiable set that is dense in X. So we all went to the talk of David Bate last week, and we know that this, in other words, implies that we barely have any Lipschitz mappings from open subsets of the disk into X. So this could happen, and somehow, in a very vague sense, Sobolev mappings are not too far from being Lipschitz, very vaguely. So it's rather surprising that we are able to construct such a map in such a generality. So this is really the hard part of the proof. And then in the next step, what we want to show is the existence of an energy minimizer, and this is a direct variational method. So we take an energy minimizing sequence, use some compactness results to show that it converges, and show then eventually the limit lies in the same class again. And in the next step, we can show that this energy minimizer has a continuous representative, and we use then results of Lipschitz and Wenger to show that it's a uniform limit of homeomorphisms, and also that it has the desired distortion property. So maybe to think about it a bit more philosophically, why should it have a nice distortion property? So if we map a ball into something that gets stretched a lot, so if it has a lot of distortion, then we also need a lot of energy to do that. So by taking the energy minimizer, in some sense, we get nice regularity results, but we also get nice distortion properties.
So when you say nice distortion property, you mean less distortion?
Yes.
Okay.
So we actually can show that this k is 4 over pi.
Okay.
So yes. And this k in some sense measures distortion. Okay. So that's the strategy. And now I want to talk a little bit about how to show that this first step that I said that is fairly non-trivial. Yes?
So can you explain what that set of functions represent, or what they are?
This lambda of x.
Yeah.
So these are sort of the candidates that we look for.
Yeah, but I don't understand the definition.
So the Sobolev map I explained, this is, I guess, fine. And then the trace is sort of the boundary map. So your Sobolev map is only defined in the disk, and what you can do is you can sort of, so as one can show that Sobolev maps are absolutely continuous on almost every curve. So what you take is you look at curves going out from like a small ball in the middle to the outside, and you sort of, these are almost everywhere absolutely continuous, and then you can sort of take the limit for going to 1 in some sense, and this gives you a notion of trace that is defined almost everywhere. And you want that this map, in some sense, has a representative that is a uniform limit of homeomorphisms. Yes. Other questions? Okay, how we construct this map is as follows. So the idea is to construct the map as a limit of Lipschitz mappings. And here we map from the closed disk into some neighborhood of our metric surface X. And this neighborhood is contained in the injective hole of X. So if you were at Martina's talk 2 weeks ago, you know what the injective hole is. If you were not there or you forgot, you can think of E of X as being L infinity of X, but it's compact. So that's why we use the injective hole here. Exactly. So you map into some little bigger space, and you have a Lipschitz map. And the Lipschitz, for every n, you get such a map into the 1 over n neighborhood. And then the Lipschitz constant might blow up if you let n go to infinity. But you choose, or we construct these mappings in such a way that they have uniformly bounded area. The uniform bound on the area eventually gives, after some reparametrization, gives a uniform bound on the energy, and therefore we can apply compactness results to get convergence. And we also want that sort of they, when we restrict them to S1, they parametrize the boundary of X. So that's the goal. Is it clear? So in the limit, it will be the map that we are looking for.
So this Vn, it really parameterizes the boundary, not only almost parameterizes.
Yes, it parameterizes the boundary. But then in the limit, you get that it's not anymore. Yes. So the idea is, first of all, is we can factorize through a 2-dimensional simplicial complex that consists of Euclidean cells of side length r over n for some r. And yeah, we want to use that to construct these mappings Bn. And well, how do we come across this simplicial complex? One can show that the metric surface under these assumptions, it has Nagata dimension 2. I think it was also mentioned in one of the lectures last week. It just means that we find a nice cover at every scale. Sort of, we find a nice cover of X. And in some sense, this simplicial complex is very similar to taking the nerve of a covering. That was also explained in one of the talks last week. And because of the way this Nagata dimension works, we can find Lipschitz mappings from X into the simplicial complex, and then from the simplicial complex into the neighborhood of X in the injective hole that are almost inverse to each other. Okay. And so, well, this follows from Jurgensen and Lang, that gives us the negative dimension 2, and then Basu, Wenger, Young, they constructed these also for higher dimensions. They constructed these sort of factorization through these simplifications. So that's what we do, and that's what we start with. That's the setting. What we want to do is we first construct a continuous map from the disk into this simplicial complex, such that the boundary of the map is contained in the one skeleton, and it is close to the image of sort of the boundary of X when we map it down with psi n. And also we want that when we integrate over the multiplicity of the function, that this is bounded by something only depending on linearly on the Hausdorff 2 measure of X and the boundary of X, the length of the boundary. Now this multiplicity here is then used to give or this inequality here is then used to give a uniform bound on the area. So by the area formula, I'm not defining area here, I know that, but in some sense this is the area of the map. So first we do that construct a continuous map. In the next step, we transform this continuous map in a way that we make it Lipschitz. And it still satisfies the properties here from above. And then once we have a Lipschitz map into our simplicial complex, we can map it back up. And because we're sort of in the injective hull, we can then extend it to a Lipschitz map of the original, let's say, parametrization of the boundary of our metric surface, and then we have the map that we want. So that's the general idea. Are there any questions? Okay. So to construct a continuous map, we first just take a homeomorphism that extends the constant speed parameterization of our boundary, and we map it down with psi n. And now, because we're in this sort of Euclidean setting, we can find a nice Lipschitz homotopy between sort of psi n composed with this eta restricted to S1 and gamma. Gamma is now a Lipschitz curve contained in the one skeleton. So we just push sort of the boundary to the one skeleton in a Lipschitz way. And we can reparameterize that, like glue it together and reparameterize it. And this, well, in the red part, it's just a homeomorphism, and the other part is somehow a nice Lipschitz homotopy. So the number of pre-images will not be huge, so we can get a nice bound as in here, this inequality. Yeah. Okay. Is this more or less clear? So this is how we construct this continuous map. Now, to make it Lipschitz, we have to choose good points in our simplicial complex. So we take a point inside a 2-cell that sort of the multiplicity of the point is less than the average multiplicity. So this is true for almost every point, or we find at least a large subset for which this is true. And also, but the other thing we want is that for any point in the pre-image of this y, we want that the winding number, so this is the winding number, is -1, 0, or 1. So what is the winding number? It's just when I take a small curve around this point, I count how many times it sort of goes around the image when I'm after mapping it. And it's a result of Rado that this is actually satisfied for, again, almost every point. So we can pick such a y that has these two conditions in this setting. Okay. Now what we do is we now pick around these pre-images X, we pick small balls, and on these small balls, there should be disjoint and everything. We define a map row n bar such that when the winding number is 0, what we do is we can just push the image of this curve of the boundary of B to the one skeleton and then extend it. So we define it on the whole ball just to be one point in the boundary. And if it's the winding number is 1 or minus 1, then we can sort of, what we do is we push the whole curve to the boundary and then extend it by Lipschitz-volume. So we get a map like a bi-Lipschitz homeomorphism on this ball B, and this sort of map restricted to the boundary is homotopic to just projecting to the boundary. So that's how we define the map on these small balls. Now it looks a little bit like that. We have all these small balls where we define the map, and in the rest of the disk, what we can do is, because now all of these sort of the boundaries of the ball have images in the one skeleton, or the boundary of one of these two cells, we can just extend it by using extension properties of the one skeleton eventually. So we just push everything to the boundary and sort of everything else gets collapsed. And since we chose our point y wisely, we still have that it satisfies this inequality 1. So the multiplicity will not be much bigger in almost everywhere of this. Exactly. So far, so good. Do we have any questions? Now, as I said before, we have this Lipschitz map into this one skeleton, and when we just can map it back up and extend it to whatever we want. So what we show is the following. We show that, okay, if we have a metric surface homomorphic to the disk, then with Hausdorff 2 measure being finite and finite boundary length, then this set is non-empty. Okay. This is sort of everything I wanted to say about uniformization. Now I want to talk a little bit about one of application of this sort of theorem. And yes.
Before you go on. So doesn't this imply that the boundary of X must be like very locally by Lipschitz to the boundary of? Because if Vn restricted to S1 parametrizes del X and Vn is Lipschitz.
Yes, you can take. We started with a constant speed parametrization of the boundary.
Yeah, so I guess how do you know a priori that there is that the boundary is so nice that you can find a...
When you're rectifiable, you can find... I mean, we know that the boundary has finite length.
So you just use the classical rectifiability theorem on it?
Yeah, and then you just take a parametrization.
Okay.
Constant speed parametrization. Okay. So the theorem I wanted, or the application I want to talk about is in terms of Lipschitz-volume rigidity. And in case you got lost, this is a very good moment to return. So the question is the
Sorry,
following.
can I ask, so when
Yes.
do you use the local geodesic in order to define the first...
Where I use locally geodesic. So I use it for having negative dimension 2.
Oh, okay.
And we also use it to make our map continuous. This could maybe be replaced, but I don't know about the negative dimension.
Okay.
Yes, but it's a very good question. We've thought about that for a while too, how to remove it, and we're not able to. Yes. Okay. So this application, the question is the following. So we have given a map between metric spaces of the same volume. And the map is one Lipschitz and surjective. And we sort of want to know, well, does it upgrade to being an isometry? Okay? Because in some sense you have the same volume, but then you have a one Lipschitz map. So, yes, so that's the problem. And it's sort of a folklore result that the answer to the question is yes, in case of X and Y being closed Riemannian and manifolds. And I say folklore because there exists proof in appendices of Burago and Ivanov an article and Dusson to Gallo, but I think it's not attributed to them as far as I know. Yes, so this is a folklore result, and what we're able to do by using uniformization is in dimension 2, actually, there are no assumptions on the metric surface needed. So it suffices to assume that y is closed Riemannian surface and x is just a closed metric surface. It could be very smooth, and they have the same Hausdorff measure, then every one Lipschitz map that is also surjective upgrades to being an isometry. So I think this is a quite nice result because somehow we don't know anything about the metric surface a priori, but just by having a nice map, we then can get much more information out of the structure of Y. So this proof, there exists a proof by Damaris and myself, and also by Basu, Marti, and Wenger by using metric currents. But both proofs they depend on the existence of a weakly quasiconformal uniformization, or of this weakly quasiconformal uniformization. And so in the work of Damaris and myself, we also get some intermediate results, which I'll tell about in a second. And I just want to mention one more thing. So there are also Duni Mati, who's also here. I mean, he's not here now, but he's around. He proved the higher dimensional variant, and there's some additional assumptions on X. So in case you're interested in these sort of questions, you should talk to Duni. Yes. So also again by using the theory of metric currents. Now, what kind of intermediate results we get? So we make the first we make an observation, namely if we have two metric surfaces of the same Hausdorff measure and this one Lipschitz and surjective map F. Then actually this map is area preserving in the sense that if we take a subset of X, A measurable subset, then the Hausdorff, this should be a 2 here, the Hausdorff measure of the image is the same as the Hausdorff measure of the original set. This is just by taking the set and sort of the complement of the set, and to both we apply to this one Lipschitz, and then we have this condition, and it follows, essentially. Okay, now what we prove is the following theorem. Namely, the theorem is more, I displayed it as a table, namely it depends sort of on the assumption we put on X or Y to what this map upgrades. So we always assume that F is Lipschitz and area preserving. Then if we assume that our metric surface X is reciprocal, so we can parameterize it with a quasiconformal map, then actually we can show that the map is of bounded length distortion, meaning that a length of curve is distorted by a multiplicative factor for almost every curve. So we can show that here again, modulus of curve family, so up to a family of curves of modulus 0, this condition holds. Now it's a question whether this reciprocality is really needed. Yes, we don't know that. How do we get such a result? So in some sense, length of curves can be obtained by integrating some notion of derivative of the map over the curve. And if we just have a map between metric surfaces, it's very unclear, Sobolev map, how to differentiate, because X is, we don't know anything about it. So if we have a uniformization map, then actually we can sort of compare the differential of the composition with the differential of the origin or of the uniformization map. And this we can use to sort of get distortion of F in some sense, how the length of curves are distorted. So that's very, very briefly what one can do, or how we use this uniformization result. Now we can show that in case Y is reciprocal, then actually the map is a quasi-conformal homeomorphism. So here, showing injectivity is rather hard, and in our work, it really depends on having two-dimensional structure. Yes, but then it upgrades to being a quasiconformal homeomorphism, which of course implies that actually X is reciprocal too. Okay. Now this upper regular here, that means upper alphas 2 regular. So we just have that the Hausdorff 2 measure over ball of radius r is bounded by some constant times r squared. And this is sort of used to find, given sort of a curve which might not satisfy that, we can find a nearby curve which does, and then show that, okay, this sort of estimate holds for every curve, and not only almost every curve. And then, what I didn't mention so far is that in these sort of results here, if we assume one Lipschitz, then we also get one BLD. But here, this is not true anymore, because there really the alphas 2 regularity constants come into play. But in case we assume that Y is Riemannian, then it actually upgrades to being an isometry. So I think this is all I wanted to say. Any questions?